Today's lesson is lesson 4, and we're talking about alternating series. In this section, this will introduce us to alternating series that contain both positive and negative terms. Let's start by looking at the harmonic series one more time. Let's consider the idea that you wanted to have the signs alternate on each term. What would you need to do to the formula to cause this to happen? So one thing I could do is I could write the summation as -1 to the nth power times 1 over n, and that would be for the first sum being negative. Or we could rewrite it as -1 to the n minus 1 power times 1 over n, and then our first term would be positive. So if we substituted in here, n is 1, we would end up with -1. But if we substituted in here, n is 1, we would get our first term being positive. So I used this approach to begin with. And then substituting n is 2, we have -1 times 1/2, so our second term is -1/2, and the summation is 1 minus 1/2, so we get 1/2, and I repeated that pattern for the first 4 partial sums and found out that my sums were 1, 1/2, 5/6, and 7/12. Then in part 2, if we use a number line to plot the sum of our new series, you can see on this black line, my first sum was 1, so we went from 0 to 1, and the second sum was 1/2, but we had to go back to 1/2, and then our third sum was up to 5 over 6, so we had to go to the right 5 over 6, and then the fourth partial sum was 7/12, so we went back. So you can see that behavior of alternating series. By the definition, an alternating series is a series whose terms are alternating positive and then negative. Alternating series can occur in 2 ways. Either the odd terms are negative or the even terms are negative. So here you see the alternating series written where a sub n is my series, and I'm alternating -1 to the n. And in this case, we did -1 to the n plus 1. So we would say that these series converge if the following conditions are met. And those conditions are that your series is positive, that your limit at infinity for your a sub n term is 0, and that your terms are decreasing. This is simply saying the second term is less than the first term, or the fourth term is less than the third term for any n. So I said it again here verbally. A series converges if its terms alternate in sign, decrease in magnitude, and have a limit of 0. This doesn't say that if the limit isn't 0, the series diverges. The alternating series test can only be used to prove convergence. It does say that if the limit isn't 0, then the series diverges by the divergence test, not by the alternating series test. And we saw the divergence test in the first 2 lessons, I believe. So let's look at a few examples. Let's determine whether the following series converge or diverge. So first thing I want to do is I want to figure out what is my a sub n term. And if you pull the -1 to the nth power off the top, you can see that our series is 1 over n squared. So if this is our a sub n term, the terms in the n is 1, and n is 2, and n is 3, and n is 4, you can clearly see that they're all positive. So we know that the terms are positive. A sub n is positive. We know that the terms are decreasing in magnitude. They're decreasing. And if you wanted to use the notation in the definition, you could, as n goes to infinity, decreasing as n goes to infinity. And we know that the limit, if you think about the limit as n approaches infinity, of our a sub n term, 1 over a very large number is going to approach 0. So therefore we could say that this particular alternating series converges. So you can try B on your own, or you can follow along with me. Here I want to see what my a sub n term is, and that looks like this is my a sub n term, since we have the -1 alternating portion out in front. And thinking about those terms, you can substitute 1 for n and get 1/2, and then 2 for n. We would have 4 in the top and 9 in the bottom, and 3 for n, we'd have 9 in the numerator and 28 in the bottom. So you can see that a sub n is positive. So we're checking the conditions. We can see that those terms are decreasing as n approaches infinity. And then we want to check the limit as n approaches infinity for our a sub n term, which is n squared over n cubed plus 1. And that's definitely 1 over n, so that's definitely heading to 0. And just like part A, this series converges. In part C, our a sub n terms, let's just go ahead and check those. This is our a sub n terms. We have 1 over 2, and then 2 over 2 squared, and 3 over 2 cubed, and 4 over 2 to the 4th. So they are positive terms. Each term is decreasing as n approaches infinity. We want to check the limit as n approaches infinity on our a sub n term. So that would be this. We have indeterminate form, and we need to rewrite that using L'Hopital's rule. So we're going to end up with the limit as n approaches infinity of 1 over 2 to the n ln 2, and that definitely goes to 0. And therefore, this series will also converge. And part D, let's see, we have our a sub n terms. When n is 1, we have 0, and then natural log of 2 divided by 2, natural log of 3 divided by 3, and so on. And if we use the derivative, we could prove that the function is decreasing. Let's see, let's use f prime of n, which is going to be 1 over n times n minus natural log of n divided by n squared. And then n is going to be e, and using the first derivative test, when we substitute to the right of e, we've got positive values, so the function's increasing, and to the left, it's decreasing. So we know that f prime of n, we know that the function f, or our a sub n term, our a sub n is decreasing based on the first derivative test. And the way I knew where the 0 of the derivative is, I took this numerator, 1 minus natural log of n, set that equal to 0. So the natural log of n is 1 when e is n, and testing to the left of e and to the right of e, so we're decreasing values. And using our properties for the alternating series, now we know that the a sub n terms are positive. We know that the a sub n plus 1 is less than our a sub n, and for all of our n's greater than e, and we know that the limit as n approaches infinity of our a sub n term is 0, and this example also converges. So all 4 of our example 1s converged by the alternating series test. And here we're going to talk about the error bound. For some convergent alternating series, the partial sum S sub n is a method that we can use to approximate the sum of the series. We'll call the error that is involved in using the idea that the sum is approximately the sum of the S sub n terms. We'll call that the remainder, where the remainder is the sum minus the partial sum. So if a convergent alternating series satisfies the condition that they're decreasing and that the absolute value of the remainder involved in finding that approximation is less than or equal to the first unused term, that means we have this statement, S minus S sub n absolute value is equal to the remainder, and the remainder is going to be smaller than the very next term. In other words, if the 3 conditions are met, it's an alternating series, the terms are decreasing in magnitude, and we have a limit of 0. If all of those conditions are met, then you can approximate the sum of the series by using the nth partial sum that we're calling S sub n, and your error is going to be bounded by the absolute value of the very next truncated term, by the absolute value of the first truncated term. Let's go see what that looks like. In example 2, if a series is alternating and converges absolutely, then the sum of the series can be approximated by adding the values of the terms with an error of the absolute value of the first unused term. There's that first truncated term. So here's our example. We have this expression, and we can show that it can be approximated to an error of 100th by adding together these first few terms. The next unused term is going to be plus, minus, so on and so forth, up to 1 over 9 squared. So our next unused term is going to be negative 1 over 100. That's where we're heading with that. It's going to be negative 1 over 100. And the error in our estimation is going to be less than 1 over 100. That's what we're going to try to show. So we want to use the calculator to find the sum of the first 200 terms. So let's go get our calculator. And with a little difficulty, we entered in x equals 1 to 200 of our expression. I combined that x n squared on the bottom and then estimated to be 0.82245. So we want to see in part 3, what is the error of our estimation from the 200 terms. So in this case, we have that summation from 1 to 200 of our a sub n is about 822,455. And looking for the error, we want the absolute value of the 200 first term. So we're looking for the absolute value of the 200 first term, and that would be negative 1 to the 202 power divided by 201 squared. And again with our calculator, so absolute value is our thing here, right here, and we've got absolute value. So we want negative 1 to the 201 plus 1 gives me 202 in the numerator and 201 squared in the denominator. And here we have our error. So 1, 2, 3, 4 zeros, 0.247. So in example 3, we're given this series, and we want to approximate the sum by using the first 4 terms. So in factorial notation, that would be 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial, and so forth until we get to the 4th term. Estimating with my calculator, I find that this answer becomes 0.625. And explain why the estimate that we found in Part A differs from the actual value by less than 1 over 100. So we can see, if you look at the terms of the series, that they alternate, they're decreasing in magnitude, and they have a limit of 0. So they meet our conditions. I'm just going to shorten this up. They meet the conditions for the alternating series test because they're alternating, decreasing, and the limit is 0. That means we could say that the remainder, which is the error is going to be the sum minus the 4th partial sum, and that's got to be less than that 5th term, or the next term truncated. So our error, absolute value, is going to be less than 1 over 5 factorial. And I'm out of room here, so 1 over 5 factorial is 1 over 120, and that's got to be less than 1 over 100. And we could show that. That's obvious there. Then in Part C, we want to use the results that we found to explain why the sum could never be 7/10. So we could say that this way: since the absolute value of the sum minus the 4th partial sum, since that's our error, and it's got to be less than the absolute value of the next term, we could think of adding this term to both sides because it's the absolute value. So it's either going to be a positive or a negative, right? So we've got that sum, and it's got to be less than, what was the 4th sum? 0.625, 0.625, and it's got to be less than 0.625. So this is 625 here. So if we leave that sum there and add it here and add it here, then this is going to be adding 1 over 5 factorial, and this would be subtracting 1 over 5 factorial. So I took that expression, broke up the inequality, and added and subtracted those two terms. So with our calculator, we've got 1 over 5 factorial, which was 1 over 120. And let's see, we're going to clear this. So we got 0.625 plus 1 divided by 120. And that's 0.63 repeating. And then we have 0.625, and we're going to subtract 1 divided by 120, and that's 0.616. So what we're finding is that the error is going to be between 0.616 and 0.633. Therefore, that total sum could never be 0.7 because it's in between 0.616 and 0.633. Then our last example, we're going to look at absolute and conditional convergence. And a series can be classified as one of the following. It can be absolutely convergent, and that means when the series converges absolutely, then the absolute value of the series converges. It can be absolute convergence implies convergence. So if the absolute value of our A sub n converges, then our series A sub n also converges. And conditional convergence says if our infinite series A sub n converges conditionally. Wait a minute, I read that wrong. An infinite series A sub n converges conditionally if our A sub n summation converges, but the absolute value diverges. So we got three things going on. And let's explore with 4 easy examples. We want to determine which of the following are absolutely convergent, conditionally convergent, or divergent. So I look at this particular series and our absolute value of our S sub n, if you look at that carefully, pulling this apart, we have the harmonic series here. It's 1 over n. And we've learned earlier that this is a divergent series. And our A sub n term is 1 over n, so it's going to meet the conditions because the terms are positive, they're decreasing. So it's going to meet the conditions for the alternating series test. We know that A sub n is positive. We know that the terms are decreasing, so it's positive and decreasing as our n goes to infinity. And then thinking about the limit, so the limit as n approaches infinity of the harmonic series is definitely 0, so it meets the conditions, but our problem is that the summation converges, but the absolute value diverges. So since our E, it's going to be conditionally convergent since we have our A sub n is convergent. Diverges, but our summation of our A sub n converges. So this one is conditionally convergent. In example B, we've got 1 over n squared, so our A sub n, actually this one over here, instead of this being S sub n, it should have been A sub n. So our A sub n is 1 over n squared, and this is a convergent P series. Since P is greater than 1, so our P is 2, so this one would be absolutely convergent by our definition. And you could walk through the steps. It meets the conditions. A sub n is positive. Our terms are decreasing and the limit approaches 0. In part C, looks like we have, this is a geometric series, so our A sub n is 0.01 to the n power, and that's a convergent geometric series. And we know that because our ratio is less than 1, it's in between 0 and 1. We know that our A sub n is positive. We know that the terms are decreasing, so A n plus 1 is less than A sub n as n approaches infinity. And the limit as n approaches infinity of 1 over 100 to the n power is going to go to 0. And this one would be absolutely convergent because the sum of a sub n and the sum of the absolute value of a sub n both converge. So absolutely converges, or absolutely convergent. Therefore, this is absolutely convergent. And then our last example, let's see, we got cosine pi n over n squared. So this piece up here, if you think about cosine is going to alternate between -1 and +1. So our numerator is our alternating portion, and our denominator is our a sub n portion. So the absolute value of a sub n is 1 over n squared, and again, we just saw that in example B. This is convergent. It's a p series, and the p is greater than 1. We've got positive terms, and those terms are going to be alternating and decreasing as n goes to infinity, and the limit as n approaches infinity of 1 over n squared is also going to 0. So therefore, this one, just like C, is absolutely convergent. So your issue is just to make sure that you're meeting the conditions each time, that you have the alternating signs, and you know whether you have a convergent series and the absolute value converges. See you next time.